we can extend the concept of calculating the area of a region bounded by a curve from rectangular coordinates to polar coordinates. Now suppose we have a polar curve where r is a function of theta, and if we define theta as the angle between the horizontal axes and our polar axes, and delta theta as the angle between these two lines that are very close, and therefore r multiplied by d theta gives us the arc length, delta s, or the length of the base of that triangle. And then 1/2 multiplied by the base by the height of that triangle, which is effectively an approximation to the area of that triangle. And therefore in the limit, as delta theta approaches 0, then the infinitesimal area of that triangle will be 1/2 by r squared d theta. And now we can integrate both sides of this equation. So on the left hand side, we get the area of the region bounded by the polar curve between some angle theta a to some angle theta b. And we can take the 1/2 outside the integral because it's a constant. And this gives us our final equation to calculate the area bounded by a polar curve between two angles. Let's calculate the area of the region bounded by this cardioid. Let's write out the area integral. So for this cardioid, we're integrating from theta equals 0 all the way around to theta equals 2 pi. And our radial function is 2 plus 2 cosine theta. And now we can expand and simplify this. And now you can use your double angle trig identity to simplify this term and evaluate the integral, and that's going to give you the area bounded by this cardioid. And post your answer in the comments. We can find the area of a region between two polar curves by extending the definite integral of finding the area of a region enclosed by one polar curve, which we derived as follows. So recall that we summed up the area of a bunch of triangular slices from some angle theta a to theta b. So let's just call this red curve, curve A. And if we apply the same definite integral to a second green curve, so the area enclosed by that curve can also be written using the same definite integral. So therefore, if we subtract the area within the red curve from the area within the green curve, then we obtain the area of this region between those curves. So therefore, our definite integral to find the area between two polar curves between angle theta a and theta b is written as follows. So typically you'd find these angles where the curves intersect, and you'll be able to evaluate the integral. Let's calculate the area of the region inside the limacon and outside the circle. So that would be this region over here. And recall that the area between curves is defined as follows. So if you substitute r equals 3 into this equation, then you can see that the curve intersects when cosine theta is 0. So therefore theta is a multiple of pi on 2. So these are the intersection points over here. So what we do is integrate from minus pi on 2 to pi on 2. And we're integrating radius of curve A squared minus the radius of curve B squared with respect to theta. And now you can expand and simplify this, apply your trig identities, and you'll be able to obtain the area.